G'day Bifrosters. Today we're looking at the point solver. Well, we're looking at making a point solver. I got this from Bruce Lee's fantastic video where he showed everybody how to set this up. And I thought I'd just pass this along to you because I've been using it for a lot of things recently and I'm really enjoying it. If you really want to get a good handle on what you can do with this, go and take a look at Bruce's video. I'll put a link in the description. We're starting off just with the usual icosphere. That of course I got from a platonic solid. I do this all the time because it's better for normals. What I'm going to do is I'm going to do things to these points and I'm going to do them frame by frame by using a solver. So let's just do some real quick setup. We'll just grab this guy and we'll get its points and normals using my node, which I should actually link for download somewhere. I'll get onto that. I'm going to throw these into a compound, which will become our solver, but for now we're just doing other setups. So I'm just going to pass it straight through. Hello, thank you. There we go. We're going to construct some points. Let me do a little bit of a point scope on this guy. We'll change them to spheres. We'll make them a little bit bigger and we will make them white. And let's pop that into the output, which of course doesn't like it. Those are possibly a little bit too big for us right now, so let's just go 0.06. There we go. Whole bunch of white spheres. Every point on the icosphere. This I'm going to call solver. We'll just do a little bit of tidy up, and then we're going to see what this solver thing can do. I'll just pop all these off to one side. What's a solver? What a solver allows you to do is make a change per frame while remembering the result of the last change. So it's how particles work. So on frame 1 there's a particle at 0, 0, 0 with a velocity of 0, 1, 0. At frame 2 that particle is now at 0, 1, 0 with a velocity of 0, 1, 0. At frame 3 the particle is now at 0, 2, 0, and you get the idea. This is just another way of doing it. It allows you to set up point solvers really quickly. Sometimes you may not want to use Bifrost's particle engine even though it's fantastic. Let's go ahead and get going. The first thing I'm going to need to bring in here is a time node, because I need to tell the solver what to do when it has no previous data, when it's at the very first frame of the sequence. At this point in time, there's nothing coming in. Well, there's the point positions coming in, but it doesn't have any data from the frame before because there is no frame before. So I'm going to throw in a little bit of logic here. So I'm going to say if, and it shouldn't be seconds, I always make this mistake, if the frame is equal to the first frame. And you can get the first frame by just clicking there and seeing what that number is. Right now it's 1. So if the first frame is equal to 1, then I'll put down, here's the logic, there's the condition, and here's the logic. If it's equal to 1, when it is the first frame, I want to give it the point positions that I passed in. And that's great. We need to do something for the false case, and this is where we start to do the solver. I'm going to jump back out of here real quick, and I'm just going to put this back into here again and then break the connection. This I'm going to be real careful. I'm going to go to set point type, set it as a vector 3 array. All good so far. I'm then going to drag that all the way over to there, break the connection, grab this one, array math float 3, because these two have to be the same. This is going to be the channel down which our solver data flows. And then I'm going to, before we go anywhere else, let's just rename these. I'm going to use Bruce's name because seriously, go watch that video, it's amazing. And then I'll delete this because I don't really, I'll delete the point positions. And here we go. I'm going to set the port feedback from output P to input P. And this is what's going to make it into a point solver. So now, what I can do is take input P and put it into the false case, which is saying if the frame time is not equal. So this is what happens when this isn't true, and this is only true on frame 1. Then take the positions from here, which is linked to this one through the port feedback. Let me show you how this works really fast. Just go back out here and we'll hook up our solver again so we can see what's going on. Just to show you what's happening, if I disconnect this and go anywhere but the first frame, I get nothing. Because the first frame, because this is true, this is coming in and going out. But there's nothing coming out for the false case. So if that frame is not 1, there's nothing to display. Now if we hook this back up, we're not making any changes to it inside of the solver. So it's just staying exactly the same. So let's make a little change to it. Let's just go in here, I'll put down an add node, I'll create a value node, and let's just give it a little change in the Y value of that vector. Now, because this changes every frame and remembers the last frame, before you do anything, or if you change anything, you need to go back to the beginning, just like a particle system. And now you can see that's happily moving up. So every point is having 0.5 in the Y added every frame, and then coming back around and going through again. So it's just a great big loop. So that's essentially how a solver works. It takes the last value from the last frame, does something to it, and spits out a value. Let's do something maybe just a little more interesting here. We'll go back to the beginning, so we reset it. Let's put down fractal turbulence. These are the incoming positions, and this is the outgoing noise. Let's add that back to the positions. And you can see already that we've got a little bit of noise. We know how fractal noise works. If we don't, let me know, and I'll do a little bit on noise to talk about noise. Actually, don't let me know, because I've got 8 subscribers, and I'm pretty sure we're all going to need to go over noise at some point, so I'll do that. That being said, you've got all kinds of settings in here that you can change. You can get more magnitude, you can get more or less frequency. I'm going to go for a little less frequency, maybe a little more than that. And now, just with those settings, let's play this. And suddenly you've got quite a cool fractal animation. Of course, I've changed something, so it's not going to show me something until I reset. Now, that's just with a piece of fractal turbulence. Perhaps that's moving too fast for me. I could just change the magnitude here. So it's not, but it's also not as big. So if I want to say, keep how big the distortions are, like this, but have them run slower, I can multiply what's coming out of there by a value. This can be a float because I want to multiply all channels of the vector by the same amount. And that amount, in this case, I wanted to make it a little bit slower. Let's make it half the speed. Pop that down there, multiply those, chain this up to the add node. And now you can see that it's still got the big movement, but it's doing it quite a lot slower. Let's make it really slow. You get much more of an idea. So of course you could hook this up as an input, and you could change all kinds of things. This is not limited to points. I've done this with strands. Bruce does it with objects in his video. You can do all kinds of cool stuff. I've done it on a plane. In fact, why don't we do it on a plane with 1,000,000 points and see how fast that runs or not. So we'll drop out here. We'll just do create mesh plane. Gonna go 10 by 10 by 1000 by 1000. We'll just hook that up. It takes a little while to sort its life out to start with, but there is 1,000,000 points in there, just over, I think. Yep, 1,000,000,2001. Just remove that. So obviously it's a little bit slower, but let's see what happens if I press play. It's still doing it, and that's not bad performance. And that's not bad performance at all. And again, if I reset that and I jump in here, And this time I can say, well, maybe, you know, it's quite big, and maybe I want a bit more frequency now. Reset that and see what happens. And, you know, I can go back to my default lighting so you can start to see like actual things happening in there. You can, of course, use a point scope, change the colors, you can do all kinds of stuff. Let's go back to our friendly sphere because that is quite slow. There's our sphere, much faster. Okay, so that's what a point solver is. Let's run through what we did. We started with some points. They can be other things, but for now it's points. I might do a sequel to this video showing you just some of the really cool things you do. In fact, I'll be doing a strand advect video at some point, hopefully soon, where I will show you what I'm using, how I'm using the solver there. Oh, and I forgot to mention you can put fields in here too. So we laid down some points. In this case it was just our friendly icosphere. We got the point positions, we put them into a compound which would become our solver, constructed points, added a point scope, and output that so we could see what we were doing. Once we had a compound that was going to become our solver, we added a time node. We did a comparison to see if the frame of the time node was the same as the first frame. If it was, we made sure we put in the points that were coming in from outside, which are these ones, point positions, coming on in. We then made one input and one output. We made sure that they were the same port type, array, math, float 3 at this point. This will work with floats and other things as well. And then we went to set for port feedback and linked up the input port, which was input P, to the output port, which was output P. And that became what happens on every other frame. At this point in time, we can do all kinds of things that we want to do to those points and add them back to the original position. And because this is now a point solver, the point comes in, is changed by the fractal turbulence, is slowed down a bit by being multiplied by 0.1, and then is added back to the original position, put out to output P. Then when the frame turns over again, output P becomes input P, and it's added again, and added again, and added again. And that's how a solver works. I hope that's helpful, and I'll see you again next time.